Okay, so we just came off talking about Euler paths and circuits. You told me in our quick little review that Euler paths and circuits cross each edge once. Okay, so we're going to talk today about another type of path and circuit by a different mathematician, an English mathematician, I believe. And we're going to talk about Hamilton paths and circuits. But before we do that, we're gonna remember making a graph. We're going to talk about our graph in addition to it. So my example that I'm going to do a couple different things with in this section is example one. Priya, she is the chief operating officer for the Hard Rock Cafe. She lives in Orlando, and she needs to visit restaurants in Atlanta, Memphis, and New Orleans. So Priya has 3 other cities that she wants to go to. She would like to determine the least expensive way to visit each of these cities one time and return to her home in Orlando. The table below represents the one-way airline tickets between each city. Now, remember, we're just doing a real quick survey. So the assumption we're making is the cost to go like from Orlando to Atlanta is the same as coming back. This is a very simplified example. You can, again, make this more real world considering different prices or different prices going back and forth or at different times. So this is adaptable to real life. But again, we're just keeping it simple because that's where we are. So what we're going to do is we're going to use this table to draw a graph. And then we're going to list the airfare between 2 cities on each edge. Okay. What this is called historically, it's called a traveling salesperson problem. And we're going to build up to the point where we do what's called a minimization of this. So here's my graph. Now remember, graphs, wherever you put your vertex doesn't matter. So if you don't know your geography, that is okay. The thing that does matter in any graph is you have the proper number of edges going to and from. So I'm going to put Orlando right here. Okay, seems to be about as south as we're going to get. I'm going to put Atlanta. Again, I'm not great with my geography. I'm going to put Atlanta here just for sake of my graph. I'm going to put Memphis. I'm going to give myself some room. And then I'm going to put New Orleans down here. Again, the orientation of the vertices is not essential. Okay, so don't get overly concerned about that. So now I'm just going to draw my edges. So to go from Orlando to Atlanta, that's going to cost me $103. So I'm drawing my edge. I'm also putting the amount on the side. To go from Orlando to Memphis, okay, so I'm going to draw this edge right here. That's going to be $161. And then from Orlando to New Orleans, that's going to be $139. Everybody tracking with me what I'm doing? Okay, this is good review because we've been gone for spring break, so we get to review making a graph. So from Atlanta, we've already got the Orlando to Atlanta edge. Again, we're oversimplifying this. You can actually, if you go further in graph theory, you can talk about one-way edges in graphs, things like that. There's lots of different things you can add to this, but we're, again, keeping it simple. So now Atlanta to Memphis, that is $229. And then Atlanta to New Orleans, that's going to be $110. Memphis, we've already got the Memphis to Orlando edge. We've already got the Memphis to Atlanta edge. We need the Memphis to New Orleans edge. So that's going to be this one right here. That's 171. And then I think by this time we have gotten everything for New Orleans. So we don't need to add any other edges. There's my graph. So the whole exercise in this first one is just drawing the graph. We're going to come back and use this graph in a few minutes. But before that, again, just to get your brain going, here's exercise 1. You've got a couple extra vertices in this one. So spread I would recommend spreading your vertices out a little more to give yourself enough room. Do your best to do exercise 1. I'm going to get started on it in a moment, just so that we can all see what we're doing here. All right, this one made a little bit of a messier graph because we got a lot of vertices, and most likely this would be the most vertices I would give you, and something you had to draw. Probably on the test it'd be fewer vertices in this, but it's a good learning experience. So you can see my mess of a graph right there. So I've got my vertices, the way I arrange them. Remember, again, I'm going to repeat this because I know it's the most common question I get. Hey, professor, my vertices are in a different orientation, or you've got this curved one from East Rutherford to San Antonio and mine cuts through the middle. That is okay. The only thing that matters about a graph is you have the same vertices going in and out, or excuse me, the same edges going in and out of each vertex. So just real quick, pointing out what I've got here, just so that you can check your work with mine. I started with the Birmingham, and I did Birmingham. So Birmingham is right here, Birmingham to East Rutherford, Birmingham to Hollywood, Birmingham to Memphis, Birmingham to San Antonio, which I've got a little curvy one here, and then Birmingham to Seattle. So as long as you've got an edge leaving Birmingham, going to each of the other vertices, you are good to go, even if they look slightly different than mine. East Rutherford, so I've already got the Birmingham one, so East Rutherford to Hollywood, so I've got this one that goes through the whole middle of this. East Rutherford to Memphis, this is the short one on mine. East Rutherford to San Antonio, I went around the outside just to stop making a big mess. And then East Rutherford to Seattle goes above the top. Again, even if your edges look different than mine, as long as you've got one edge going from East Rutherford to all those places, you're good. Hollywood to Memphis cuts through the middle on my graph. Hollywood to San Antonio comes just a short little edge here, and then Hollywood to Seattle cuts the top. Memphis, right here, kind of in the middle, probably not the best place I could have put that. Memphis to San Antonio cuts right through here. And then Memphis to Seattle, diagonals up. And then lastly, San Antonio to Seattle. So San Antonio, Seattle just cut right through the middle. Are we okay? Are we seeing? I know that's kind of a mess there. Are we doing okay drawing the graph, though? Any issues? All right, well, be ready to come back to that. We'll refer to that page again. Okay, so those graphs that we just drew, you notice that we added values to each of the edges. So what we created is called a weighted graph. And what that is, a weighted graph has a value such as a cost or a distance or anything other value that would be appropriate to your situation. So a weighted graph has a value associated with each edge of the graph. And so you can see that if you turn back to the front, you can see that on both the graphs we just drew, that each edge has associated with it a particular dollar value. That's what makes it a weighted graph. One of our examples coming up, you're going to do one that's going to have distances associated with the edges. That makes it a weighted graph. There's other situations, but in this class, either cost or distance are going to be the most common thing. So that then takes us to where we are in our purpose for being together today, a Hamilton path and circuit. So again, we reviewed what an Euler path and an Euler circuit was. That is one that you cross each edge one time. In a Hamilton path, that's a path that contains each vertex exactly one time. I want to make a little note, okay, about this. That means it's okay to skip edges in your Hamilton path. You're not going to get, most likely, you're not going to get to every edge. Okay, there's going to be some that you leave out. And that's okay, because the purpose of a Hamilton path is you are now concerned about the vertices, not the edges. Okay, that's the difference. A Hamilton circuit is a circuit that passes through all the other vertices exactly once. The only vertex that you repeat in a Hamilton circuit is the one that you start and you stop at, okay? You will repeat that one because that's the definition of a circuit. But all the other vertices you're going to go through once. Again, it's okay to skip edges. You're not going to get to every edge in a Hamilton path or a Hamilton circuit. So right below that, exercise 2, I would like you to determine 2 different Hamilton paths, okay? Doesn't matter where you start. I would suggest picking a different starting spot for each of them, but determine 2 different Hamilton paths on that graph. You just want to get to each vertex one time. All right, somebody give me their Hamilton path across this graph.
A to B, B to C.
Okay, hang on, you got to slower. A to B.
B to C.
B to C.
D to I.
Where do we go from C?
Oh, C to D. I'm sorry.
Okay.
C to D, D to I.
Okay.
I to H.
Okay.
H to G.
Okay.
G, I had to hit B again.
So that makes it not a Hamilton path.
Well, so it was just not a circuit. It was a path.
Nope, you only hit each vertex one time. Okay, so nice try. That's okay. We're learning. That's what happens when you learn. Okay, give me one. What do you got?
G to H.
So you said D to H.
G.
Oh, G to H. Okay, sounds great.
H to I.
H to I.
I
To
to D.
D.
To C.
Uh-huh.
To B.
Uh-huh.
To F.
Uh-huh.
E, and to A.
Perfect. There you go. So that hits each vertex one time. Notice it didn't go over each edge once. Doesn't have to. Edges don't matter in Hamilton path circuits. Somebody give me another one. Go ahead, Paula. Great. Really, whatever you got there, the only way you're not going to get one is if you start on this side and then you hit this. You see how everything goes to this vertex right here? If you hit that vertex before you've done all the others, that's going to be a problem. Okay, no big deal. Doing good. All right, exercise 3. Determine 2 different Hamilton circuits. So again, each vertex once, except for where you start and stop. Who wants to give me one?
I'll try it out.
Let's go.
Let's see if I can do this. All right, D to B.
All right, so D to B, great.
B to A.
Uh-huh.
A to C.
Uh-huh.
C to F.
Sure.
F to H.
Uh-huh.
H to E.
Yep.
E to G.
Yep.
G to D.
You did it. Great job. You hit each vertex one time. Somebody got something different for me? I know, spring break. You lost all your energy. No one wants to talk to me anymore. Basically, if you pick any vertex on the edge, just go around the outside of this figure, you're going to be fine. Here's something else. I'm going to start at H and then go up to F. And then I'm going to cut over using that little one that cuts between that square over to E, and then to G, and then around the outside, D, B, A, C. Oh, I didn't do it. I got all happy with myself and I messed it up. Good job, Perkster. So I'm learning too, just like you're learning. Let me start at F then. And basically, I'm just going to cut around the outside like I probably should have done, but I was trying to be tricky and fun. But there we go. So if you pick any vertex on the outside and you just cut the outside, you're going to be just fine. Any questions so far about the difference between those two things? As you're looking through your list, if you didn't give me yours because you're feeling all shy and silent today, remember, when your Hamilton path, you should have every letter in your path and nothing should repeat. In your circuit, you should have every letter. The only one that repeats should be the endings. Okay, the beginning and the end should be the same place. If you have any question about whether yours is or is not, feel free to wave that hand in the air. I'm happy to do whatever I can. So notice it can be a little bit difficult. Do I have a Hamilton path or a Hamilton circuit? Like you were just trusting that you were going to be able to find one because I gave you the example. And so we know when we talked about Euler paths and Euler circuits, it was knowable if I could do it. And so what we're going to do when we're talking about Hamilton paths and Hamilton circuits is we're going to limit ourselves to something specific. We're going to talk about what's called a complete graph. And what makes a graph a complete graph is that it has exactly one edge between each pair of vertices. Okay, there's one edge between every pair of vertices. That's what makes it complete. So notice the graph that you can still see on my page. Why is that not a complete graph, the one that I'm pointing to? E does, but does E have an edge going to every other vertex?
Oh, no.
No, it doesn't have one going to A, and A doesn't have one going to D and to F and everything. So a complete graph has to have an edge that directly connects every vertex. Okay, so that's why this one's not complete. Go back to the front page. Both of the graphs we drew on the front page are complete graphs. So notice on my example that I did for you, there's an edge that connects every city. Orlando, you can get directly to Atlanta and Memphis and New Orleans, and the same thing for every one of the other vertices. And the example you did, exercise 1, that is the big messy graph. Okay, even though it's a big mess, I can get from any vertex to any other vertex directly. That's what makes something complete. Okay, everything is joined together directly. And so the reason we care about complete graphs is every complete graph has a Hamilton circuit. If every edge is joined, if every vertex is joined directly, then you can find a Hamilton circuit. So for exercise 4, when you're done having the joy filling in those blanks on that previous one, then go ahead and exercise 4, determine a Hamilton circuit. There's lots and lots of options once you have a complete graph, which we do there. All right, somebody give me your Hamilton circuit for exercise 4. Go ahead. Okay, A to B to D. Are we going back? We're going back to A already? Okay, so remember, in a Hamilton circuit, I want to hit every vertex. Okay, did you say we started at A? Okay, so if I go A to B to D, I can't go back to A yet because I have E and C that I need to hit. Okay, so let's just keep following your trend. You were going around the outside. That sounds fine. So then let's go from D over to E. And then we'll go E to C. And then C up to A. So we just followed the outside of that, and there is a Hamilton circuit. Okay. Yeah, you got it. I understand what you're doing, and that's why I'm asking you for yours, is so we can learn. That's what we're all about here. How about another one? Who's got one? Go ahead.
A, D, C, B.
So yeah, following the star on the inside instead of the outside. Great. And there's any combination of those things that you can do. In fact, we could figure out how many Hamilton circuits there are on a complete graph. That is our next exercise. I'm going to flip back and forth between these two pages. But what we're going to do at the top of the next page, there we go, is we're going to figure out the number of unique Hamilton circuits in a complete graph. So I'm just going to flip back to that previous thing. And in fact, I'm going to do my work here and then I'll transcribe it so that I don't have to keep flipping pages on my video. Let's just say we're going to start at vertex A. That seemed to be what both of my examples given to me did. So if I'm at vertex A, first off, how many vertices does this figure have? It has 5. Okay, so I've got 5 vertices. If I'm at vertex A, how many choices do I have of places to go? Okay, yeah, I can go to B, I can go to D, I can go to F, I can go to C. I can go any of those places. So I have 4 choices there. Okay, so let's say I go from A over to B now. Now I can't go back to A because I haven't done all the vertices yet. How many choices from B do I have to go to now? 3. I could go to D, I could go to E, I could go to C. I'm not going to go back to A because I'm not ready yet. I haven't visited all the vertices. So I have 3 choices. So we've gone from A to B. I'm just going to put a little mark there so I know. Then I've gone from B. Let's just pretend I'm going around the outside. Let's pretend I'm gone over to D. Okay. Well, now I'm at D. We started at A. We went to B. We're at D. How many choices do I have of vertices to go to now? 2. I can only go to F. I can only go to C because I'm not going to go back to B because that would be repeating. I'm not going to go back to A because I haven't done all the vertices yet. I'm not ready to go back. So I have 2 choices. So let's say I make the choice to climb over here to vertex E. Now I'm at vertex E. We started at A. We went to B. We went to D. We went to E. How many choices do I have from here? I only got that 1 vertex left. I only got vertex C left. And then from C, we have to complete the circuit and go back. Now, I don't know how many of you took MGF 1106. I know it's not a prerequisite for this class, okay, but generally students do, but in case you didn't. What this is called, when I start at a number and I just multiply by every whole number down, this is called a factorial, in case you don't remember. Those of you who are in 1106 right now, this is coming up, so you haven't seen it quite yet. And so what we've got here, the way I would abbreviate this is I have 4 times 3 times 2 times 1. That's 4 factorial. That's 4 with an exclamation point. On your scientific calculator, if you've got an exclamation point, that is the factorial. It does not mean to say 4 really loud, like 4, yes! No, it's just saying 4 factorial. So 4 times 3 times 2 times 1, when I do that multiplication, or if I put that into my calculator, 4 times 3 is 12, 12 times 2 is 24. So when I had 5 vertices, the number of unique Hamilton circuits I could do is 4 factorial. It's 1 less than the number of vertices. And here's what I'm going to write up here at the top of the next page. The number of unique Hamilton circuits on a complete graph. If we have n vertices on a complete graph, so if we have n vertices, n is just a number, whatever number you'd want it to be. If we have n vertices on a complete graph, then the number of unique Hamilton circuits is given by this. And I'll give you a second to write this down. I know this is the most writing you've done in this class in a while. It's given by n minus 1 factorial. So you take the number of vertices, you subtract 1, and you make it the factorial. So on the previous one, we had 5. So 5 minus 1 is 4. That's where the 4 factorial. And then you could either just do that by hand, 4 times 3 times 2 times 1, or you could find the exclamation point on your calculator. If you don't know where your exclamation point is on the calculator, just wave your hand when we're doing the next couple problems, and I will help you find it. Okay, that way it shortens the amount of work you have to do. So I'm going to do example 2 just to get us into the habit. Example 2 says how many unique Hamilton circuits are in a complete graph with 7 vertices. Okay, so since it has 7 vertices, according to what I just told you, the number of unique Hamilton circuits is 7 minus 1 factorial. Okay, so there's 7 vertices. That's where that 7 came from. 7 minus 1 is 6 factorial. If you just have a plain old 4-function calculator, then what you're going to do at this point is go, oh, okay, that's 6 times 5 times 4 times 3 times 2 times 1. Or if you have a calculator that does the factorials, if you have any sort of Texas Instruments calculator, you have a button that's labeled PRB. It's the probability button, and it should lead you to a menu to be able to do your factorial. If you don't know where that is, again, let me know. I will help you find it in just a minute when we're doing our next couple of examples. Okay, so 6 times 5 is 30. 30 times 4 is 120. Times 3 is 360. Times 2 is 720. Correct me if I'm wrong on that if you got your calculator. There's 720 unique Hamilton circuits from that. All right, so what I would like you to do is do the next 2 exercises, exercise 5, exercise 6. And if you need help using your calculator, raise your hand and I'll come right over to you. Oh, great job. Well, it takes me a second on this one. So if you want to do 6 factorial, 6. Hit the math menu. See the top of the math menu. There you go. Anybody else? Okay, again, if you're just too shy, you can see me after class. I'm happy to help you find that. It makes your calculating life a lot easier. So exercise 5 says how many unique Hamilton circuits are in a complete graph with 10 vertices. So this is going to be a large number. So that's going to be 10 minus 1 factorial. So that is 9 factorial. And so again, if you don't have an exclamation point, if you don't have a scientific calculator, then you're going to do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you do have the exclamation point, what is that value?
362,880.
362,880. Do I have confirmation of that? Everybody agree? Yeah, that's a lot of Hamilton circuits. I asked you to do the same thing in exercise 6. I said how many unique Hamilton circuits are in the complete graph from your exercise 1. So we go back to exercise 1, the one you did. How many vertices are on this graph of exercise 1?
6.
Not example 1, exercise 1, the one down at the bottom. If you did example 1, then yeah, it would be 4, and 4 minus 1 is 3. So there'd be 6 that you could do. So I'd give you credit. Exercise 1, we've got 1, 2, 3, 4, 5. We've got 6 vertices. So that means that there are 6 minus 1 factorial or 5 factorial Hamilton circuits. So in a minute, when we go to do our minimization problem, our traveling salesperson problem around that, there's going to be how many? 5 factorial is what? 120? There's going to be 120 unique Hamilton circuits that we could try. That's a lot. Okay. We good so far? I feel great. I'm loving it. I love the graph theory unit. This is my favorite one, so I'm having a great time. So the next thing, the weighted Hamilton circuit with the lowest associated value, whether it's cost or distance or whatever, is that is called the optimal solution. So since we're not doing this class with a computer, okay, so the way that we're going to find the optimal solution is to use what's called the brute force method, which I will not give you the brute force method with anything more than 4 vertices. Okay, again, my goal here is not to math torture you. Okay, I'm just trying to teach you an appreciation for math. Okay, what the brute force method means to do is we are going to go through and we're going to list out all the possible Hamilton circuits and see which one of them is the lowest cost. Okay, so you can see why I'm not going to give you that for more than something with 4 vertices, which has 6 possible Hamilton things. So rest easy. So example 3 says, use the brute force method to determine the optimal solution for example 1. So we're going to help Priya from example 1, and we're going to help her find the optimal solution. So what we're going to do here with Priya is she's starting in Orlando. So we're going to list out all 6 possible options for her. So first thing we can do is Priya can go, and I'm just going to try to do this in a way that keeps everything nice and clean. Priya could go from Orlando to Atlanta. So I'm going to come over here to my work. She can go from Orlando to Atlanta. We'll fill in the weights in just a minute. From Atlanta, her choices are she can go to Memphis or New Orleans. So let's say she goes to Memphis, then she has to go to New Orleans, then she's visited all the cities, so she goes back to Orlando. There's option 1. Option 2, I'm going to again take Priya from Orlando to Atlanta, but this time instead of going to Memphis, I'm going to reverse those and go from New Orleans to Memphis, then back home. So that is all of the Orlando to Atlanta routes we could take. So now what we're going to do is instead of Orlando to Atlanta, we're going to go Orlando to, what's the next one as I'm roving around? Instead of Orlando, Atlanta, we'll go Orlando to Memphis will be next. So we can take Priya from Orlando to Memphis. And then from Memphis, we can go to Atlanta, to New Orleans. That's all the vertices. So to complete the circuit, we go back home. Again, I can take Priya from Orlando to Memphis, but this time, instead of going to Atlanta like we did in the previous one, we're going to flip-flop these 2 and go to New Orleans to Atlanta. We're going to see, does that affect the cost? And then home. Does everyone see what I'm doing? I know it's boring. It's just a little bit of labor. Okay, but there's 6 options we have to account for. So we've done all the Orlando to Atlanta routes. We've done all the Orlando to Memphis routes. The last one is I've got Orlando to New Orleans. And then from New Orleans, Priya can go to Memphis and then back to Atlanta. And then that's all the vertices. So we complete the circuit. And then last but not least, instead of going from New Orleans to Memphis, I can flip-flop those 2 and go to Atlanta, to Memphis, to Orlando. Okay. Those are the 6 things that can happen. Those are Priya's only 6 options if she wants to go to each of these cities, each of these vertices exactly once. Now, this is why it's called brute force, as you're going through every option. Now what I'm going to do is I'm going to fill in the weights from my graph. I am going to cheat a little bit so that I don't make the people watching on the video more dizzy than they already are, is I'm just going to grab another table right here, and probably should do this the next time I print this. I'm learning as I go. So here's what I'm going to do. I'm going to fill in the weights. So to go from Orlando to Atlanta is 103. To go from Atlanta to Memphis, that is 229. These are all the weights on the graph. To go from Memphis to New Orleans, that is 171. And then to go from New Orleans back to Orlando, that's 139. So this takes a moment. Sorry. The next one, Orlando to Atlanta, is 103. Atlanta to New Orleans is 110. New Orleans to Memphis is 171. And then Memphis to Orlando is 161. Orlando to Memphis is going to cost us 161. Memphis to Atlanta is going to cost 229. Atlanta to New Orleans costs 110. And then New Orleans back home to Orlando, it costs 139. Orlando to Memphis, got that. Memphis to New Orleans is 171. New Orleans to Atlanta is going to cost 110. And then finally, Atlanta back to Orlando is 103. And now we're down to the last two routes. And if you're reading this from the graph, that's even easier than reading it from the table. That's why you make a weighted graph in the first place. So Orlando to New Orleans is 139. New Orleans to Memphis is going to be 171. Memphis to Atlanta is 229. And then Atlanta back to Orlando is 103. And last but not least, finally, New Orleans to Atlanta is going to be 110. Atlanta to Memphis is going to be 229. And then finally, Memphis to Orlando is 161. Woo. Last thing to do is we're just going to add those up. So if you can help me. Don't want to say a whole lot of names since I'm recording. So if these rows, if you could do the first two, the Orlando to Atlanta, if these rows could add up the next two, Orlando to Memphis, and then these rows, if you could do the last two, the Orlando to New Orleans, add up what those two totals will be, and then we'll write them down and we'll see what's the lowest amount of money that Priya is going to pay. That's how we're going to do it. So I'll give you a moment. I appreciate you pressing the calculator buttons for me. All right, so the first one, the top one, Orlando to Atlanta to Memphis to New Orleans to Orlando. What is this total cost right here? 642? Do I have confirmation from that row? Great. And then the next one, Orlando to Atlanta to N to M to O, what's that one? 545, okay, so we've already got a price difference. Great. Next two rows. What's this one? O to M to A to N to O. What does that equal? 639, okay? If anybody gets something different, let me know, but I'm going to trust what we've got. So then O to M to N to A to O, what does that equal?
545.
Okay. And then last two rows, O to N to M to A to O, what does that one equal?
642.
642. And then O to N to A to M to O is 630.
I got 39.
I think it should be 39. I only say that because since we're dealing with the simplest possible situation, you can see that they double up. But again, the reason I have you go through all of them is if we real worlded this a little more, you know, there can be price differences going different ways. So that's why we're just going through the whole thing. So we see that the cheapest thing Priya can do, and she could do two different routes, is $545. So she can either go from Orlando to Atlanta to New Orleans to Memphis back to Orlando, or Orlando to Memphis to New Orleans to Atlanta to Orlando. Those two routes cost her $545. All right, we're almost done. You're doing a great job. Here's the longest problem you've got left. The other method is going to be a lot shorter, and it's going to be an approximation. But before we get there, exercise 7 says this. The State College of Florida Student Government Association, they are in Bradenton, or Bradenton, however you say that, and they're planning a trip over their break. They're going to visit Washington, Montgomery, and Savannah. The distances in miles between all those different places are given to you. Here's what you're going to do. You're going to do two things. First thing you're going to do is you're going to draw the weighted graph. It's got 4 vertices. Okay, so draw the weighted graph like we had for the previous problem. And then I want you to do the brute force method on what is the shortest driving distance that this group has to visit all of those cities. Okay, I'm going to give you 4 or 5 or 6 minutes because I know that the brute force method takes a little bit of time. If you're watching on the video, I'm going to pause the video, so go ahead and pause yourself while you do the problem and then start it back up. All right, so here's my graph. Got my 4 vertices. Again, I'm going to have you do one of these on the test, but it'll only have 4 vertices, okay? Because then if we up it to 5 vertices becomes 24 options, and that's way too many to do the brute force method without a computer and a spreadsheet or something like that. So here we go. Here are the 6 different routes this SGA group could take. So they go from Bradenton to Savannah to Washington to Montgomery home, then Bradenton, Savannah, Montgomery, Washington, home, etc. You can read all the 6 different options. So then I filled in the various values, and I got that the shortest route, and of course it doubles up, the shortest route is 2,255 miles. They can either go from Bradenton to Montgomery to Washington to Savannah back to Bradenton, or they can flip-flop the Montgomery and Savannah in the order there in the very top. Those are the 2. Anybody get something different that we need to talk about? I know it's a bunch of busy work, so I'm not like super fan of those problems, but it's helpful to get to understand how the graph's working. Okay, well then we're flipping to the last page. If you have anything for me beyond that, let me know. So for a graph with a lot of vertices and you don't have a computer, for us, it's going to be more efficient to use what's called the nearest neighbor method. And what the nearest neighbor method yields for us is an approximate solution. On your page, I copied and pasted the book's chart on how to do the nearest neighbor method. Basically, just to summarize what that chart says, all you do for the nearest neighbor method is you pick the edge with the lowest cost. Okay, so you pick the edge to a vertex you haven't been, with the lowest cost. Or I'm going to say lowest value just in case it's not a cost problem. Okay, that's the summary of the nearest neighbor method, but I gave you the whole thing in case you're a detail person and you like lists. Well, then you got the whole list there. So once you finish that, I'm going to finish up, or actually, you know what, I'm going to have you finish up. First, you're going to do exercise 8 for me. And you're going to go back and you're going to use the graph on page 1 for that one at the bottom with the 6 vertices. And you're going to use the nearest neighbor method. You're going to do the best you can to approximate the cost of travel to each city, assuming you'd like to begin and end in Hollywood. So again, you're going to start in Hollywood, and what you're going to do first is you're going to pick the edge that has the lowest cost and go there. And then of the remaining choices, once you're in that new place, you're going to pick the edge with the lowest remaining cost. Remember, you do not want to visit anywhere more than once. We're learning. If you get this first one wrong, it's okay. Okay, so you start off in Hollywood. I'm just going to make the Hollywood vertex green, so I know that's where we're starting. And you have 5 choices. You could go to Seattle, you could go to East Rutherford, you could go to Memphis, San Antonio, or to Birmingham. Which one of those edges has the lowest value?
Yeah.
Is that what you said? Yes, to Seattle. Perfect. And the Hollywood to Seattle costs 108. Now I'm in Seattle. Now remember, I don't want to go back to Hollywood. I've got to do a Hamilton circuit. I've got to go to every vertex. So I'm in Seattle. I can go to San Antonio, that's 119. I could go to Birmingham, that's 135. I could go to Memphis, that's 299. Or I can go to East Rutherford, that is 154. Which one of those is cheapest? The San Antonio. So I'm going to spend 119. Great. Now we're in San Antonio. So again, I don't want to go back to Seattle. I don't want to go back to Hollywood. So my choices are becoming more and more limited. I can go to Memphis for 634. I can go to Birmingham for 274 or East Rutherford for 355. So clearly the cheapest choice is to go to Birmingham, and that is 274. Great. So now I'm in Birmingham. I've got 2 cities left to go to. I can go to Memphis for 324 or East Rutherford to 258. True. East Rutherford for 258. Now at this point, I am predestined because there's only one vertex I haven't visited. So I have to now go to Memphis, and that's going to cost me 104. So that's serendipity for me. Great. And so then from Memphis, again, I only have one choice because to complete the circuit, I got to go back to Hollywood. And Memphis to Hollywood is 144. And when I add all those up, how much are those plane fares going to cost me to get around my circuit? 1,007? 1007. Do I have confirmation of that? Sounds good to me. Okay. So we've got about 11 minutes left in class. That should be plenty of time. What I would like you to do to finish our time up is I've given us one more chart. Exercise 9. This time we just have 5 vertices, so it's a little bit better. I want you to create the complete weighted graph of that, and then use the nearest neighbor method to help Miriam, who lives in Boston, visit each of those cities and return to Boston. Again, if you're watching on video, I'm going to pause this for a couple minutes so that you're just not listening to silence. Keep working. I'm just going to get started on my weighted graph to save us a little time. If you have any questions at all, please ask. We're gonna make a circuit.
Like, sort of box. How I know. I'm supposed to. This one.
Because the context of the problem, so Miriam lives in Boston, and so Miriam needs to visit all these farms, and so I didn't say it explicitly, so I'll be sure to do that on the test, but Miriam wants to visit the farms and then go home. So she's gonna leave from Boston, and then to complete the circuit, she's gonna make her travels back home.
Assuming the test you didn't draw out everything.
I would want to see, I understand that you can do the problem without drawing it, but I would want you to, just because we're talking about graph theory and constructing them and everything. So but by me, instead of me giving you a vocabulary question, I just say, make the complete graph, the weighted graph. So then you know, that helps me know, you know what that is. That's why. Okay, so let's finish this up. There's my complete weighted graph. Remember, complete graph means each vertex connects directly to another edge. It's weighted because all the values. So Miriam is going to start in Boston. So we're going to start in Boston. And then what's her cheapest flight leaving Boston of her choices?
Madison.
Okay, she's going to go to Madison for 131. Great. Now she's in Madison. What is the cheapest flight of the options there? Go to Princeton for 154. Great. Now she's in Princeton. And what's her cheapest option from Princeton? Salem. Salem for 353. We doing okay? Have I made any mistakes or anything? Make sure. All right, we're in Salem. We've got basically we only have one option now, so it's good that it's not an expensive option. So we got to go to Walla Walla. And then last but not least, she has gone to each vertex. She's ready to go home to Boston. And so that's 576. And when I add up all those 5 flights, what is Miriam's total going to be? 1,000, how many hundred? 1,393. So that is an approximation of the optimal solution.